this question, we are given the band diagram of a p-type semiconductor of band gap 1 electron volt, and we are also given the information on the threshold voltage, oxide capacitance, metal work function. It also states that there is no charge within the oxide and that the voltage applied across the capacitor is VTH. We are asked to calculate the depletion charge per unit area. For detailed explanation regarding this topic, watch the NPTEL course given below. Before we proceed with the solution, we need to have knowledge on the bulk potential, surface potential, work function and threshold voltage. If you are confident with these topics, feel free to skip this section of the video. Let's start with the band gap. Band gap is the energy required by an electron to reach from valence band to conduction band. We know that in the intrinsic semiconductor, the Fermi level lies at the middle of the band gap, whereas in a doped semiconductor, the Fermi level shifts to either side of the intrinsic Fermi level. If it's p-type, it's closer to the valence band. If it's n-type, it's closer to the conduction band. So that shift in the Fermi level with respect to the intrinsic Fermi level is termed as a bulk potential. So let's say if you have a p-type semiconductor where your Fermi level is closer to the valence band than to the conduction band, this shift from the intrinsic Fermi level is termed as a bulk potential. Okay, so the Q times IB would be EI minus EF. Before we talk about surface potential, let's consider a scenario where the MOS capacitor is operating in inversion region. When you say inversion region, it means that for a p-type semiconductor, the surface is more n-type than it is p-type. So that is, the concentration of the electrons on the surface is more than that of the holes. And then you would term it as a strong inversion region if the surface is as n-type as the substrate is p-type for a p-type semiconductor. So in the strong inversion region, bands would bend in such a way that the Fermi level is closer to conduction band than to the valence band. Okay, and then the Fermi level at the surface is located as much above the intrinsic level as it is below the intrinsic level in the bulk. So we have looked at this is Q times IB. So this is Q times IB in the strong inversion region. So the surface potential psi S is 2 times psi B. Coming to the work function gives you the difference between the Fermi level and the vacuum level. Okay. Let's consider it for a metal. You have a vacuum level EVAC and the Fermi level EF. So the metal work function would be EVAC minus EFL. Whereas in semiconductor, let's look at p-type semiconductor. So the difference between the energy levels of the vacuum level and the conduction level is your electron affinity Q times Is, and EC minus EI is Eg by 2 and EI minus EF is Q times psi B. So we know that the work function of the semiconductor would be the difference between the vacuum level and the Fermi level. So that would give Q times phi S is Q times psi S plus Eg by 2 plus Q times psi B for a p-type semiconductor. Okay, if it is an n-type semiconductor, you know that the Fermi level is above the intrinsic level. So that would be Q psi S plus Eg by 2 minus Q times psi B for an n-type semiconductor. Okay, so the metal semiconductor work function phi ms would be phi m minus phi s. Flat band voltage is a voltage that needs to be applied to make the bands flat. We can compute this by evaluating the difference between the two terminals that we have. So that would be the flat band voltage VFP is phi ms minus QF by Cox. That is, if you have any oxide charges, so you would consider that to apply to the MOS capacitor, drops across the flat band voltage plus psi ox and psi s. Psi ox, which is the potential across the oxide layer, and psi s, which is the potential across the depletion layer in the p-type semiconductor. The potential across the oxide layer would be minus Qs times Cox, where Qs is a total semiconductor charge density. And the total semiconductor charge density would be the sum of the depletion charge density and the inversion charge density. But in our question, it's stated that it's operated at the threshold voltage. So it means that the inversion charge is 0. So Qs is Qd and Ψox is minus Qd by Cox. And so the final equation, that is the applied voltage Vth, is VFP, that is phi ms minus Qd by Cox plus psi s, which is 2 times psi b. We are given the information on the band gap. So we have learned that the band gap is the difference between the conduction band level and the valence band level. So the same thing, we can write it as EC minus EI plus EI minus EF plus EF minus EV. From the figure, we know that the EC minus EI is Eg by 2, that is 0.5 electron volt, plus EI minus EF is Q psi b, plus EF minus EV is given as 0.2 electron volt, which would sum to 1 electron volt. So from this, we know that the bulk Q psi b is 0.3 electron volt and the bulk potential is 0.3 volt. And the surface potential psi s is 2 times psi b. So that is 2 times 0.3, that is 0.6 volt. In the question, it's given that the applied voltage VGB is Vth. So Vth is VFP plus Ψox plus Ψs. VFP is phi ms, Ψox is minus Qd by Cox plus Ψs is 2 psi b. So to calculate the magnitude of the depletion charge density, so we need to calculate the metal semiconductor work function difference as well. Let us calculate the semiconductor work function, that is EVAC minus EC plus EC minus EI plus EI minus EF. So your semiconductor work function is 4.8 electron volt. Semiconductor work function difference is phi m minus phi s, that is 3.87 minus 4.8 minus 0.93 volt. Okay, so let's substitute this value. We are given the threshold voltage is minus 0.16 is equal to minus 0.93 minus Qd by Cox plus 0.6. So Qd by Cox So the magnitude of the depletion charge density is 1.7 into 10 power minus 8 coulombs per centimeter square.